Hi everyone! In the previous video, we started the implementation of a search flight aggregator. Now we are able to contact two different data providers and combine their results. It's good, but our application will need to do more than that. For example, when I search for flights between London and Paris using the website Skyscanner, they reported using 29 data providers. Okay, so let's have a look at the implementation of from to clients. It would be relatively straightforward to add a third, fourth, or fifth client to this method. Each client will need to be passed as inputs over there, and then within the for comprehension, we need to add one line per client, like this. This should work fine, but we wouldn't want to repeat this process 29 times. It would be extremely repetitive and error-prone. Additionally, we may not know in advance the number of clients. For instance, it's likely that the clients are defined in a configuration file that the application loads when it starts. Okay, so instead of adding more inputs to this method, we are going to implement a new method called fromClients. You can find it a few lines further down. So fromClients create a search flight service from a list of clients. This means that we don't know how many clients are passed as inputs. The list could be empty, or there could be dozens of clients. The only assumption we can make is that in practice, the list shouldn't be bigger than 100. Now it's going to be your turn to implement and test fromClients. I recommend that you either use a recursion or fold left to iterate over the list. Please pause the video and give it a try. So I suggest that we start by adding tests to this method. What we could do is copy-paste the test we have from to clients. From to clients is very likely that later on we'll either get rid of it or re-implement it in terms of from clients. But for now, let's just copy-paste and we can clean it up later. So say from clients, and that's it. So here in this case, we want to use a list. And in this case, we also want to use a list. Actually, instead of doing this for the error case, at the moment we generate two clients and we pass it to fromClients, we could also use our list generator. So we could say gen list of and pass client gen. So this way we let the property best framework to generate the list of clients for us. So it will generate sometime 0 clients, sometime many clients, we don't really care. Let's rerun the test. Yep, it fails. And in fact, we could even add more tests to this. For example, now it's a bit easier actually to have a list as an input. Now it's a bit easier to write property-based tests for this. For example, we could say that the order of the clients don't really matter. So how will we test such a thing? We can say from clients, so client's order doesn't matter. And how do we verify that the client order doesn't matter? We can just create two services. So one will be from the list of clients that we get from the property-based framework. And then we can randomize this list of clients. So in the random object, so random is used to generate an int or a string or something like this. But there is a method called shuffle. And shuffle takes a collection and gives you back a new collection where all the elements are shuffled. So now when we have this, we could say, okay, let's run the service 1 and service 2. So let's run these two services. With the one will have the normal list of clients, the other one will be all shuffled. And we can verify that at the end, we expect to get back the same result. So this could be a test that is actually much simpler to write using property-based test, using a list as input. So let's rerun the test. Cool, so the last three fails because we haven't implemented fromClients. Let's do that now. So how do we implement this method? Well, it's likely that we will need this search by client because search by client is a helper method that we define in order to tell us how to search for a single client. So Now there are a couple of strategies we can do here. So I suggest we start with the simplest one, at least in my opinion, the simplest one is a basic recursion, and then we'll refactor it a couple of times to arrive to something quite nice at the end. So how could we use a recursion? So we have a list of clients. So because a list is an enumeration, we can always use an exhaustive pattern match. And what's nice with an exhaustive pattern match is that we go from one complex problem, finding out, calling like, so search for a list of clients, to two relatively simpler problems. One where we have to deal with when the list is nil, and one when we have a client and potentially a list of others. So this is a client, and this will be other clients. So the simple case is when the list is empty, because if the list is empty, we know the result. It's going to be a search result with an empty list of flights. You know, if we don't have any clients, we can't really search anything. We can't come up with artificial flights. Actually, and so here we're going to do like a recursive case. What might be good is to define another helper method, because if you see here, we're dealing with search result, and search result is essentially a wrapper for a list of flights. But we could deal with the sorting and uniqueness all at the end. We can first collect all the lists, and then at the end, you know, deduplicate and reorder everything. It will be slightly more efficient, but also easier to implement. So let me show you what I have in mind. So here it is going to be search all clients. So search all clients is going to take a list of clients as the input, and it's going to give us an IO of list of flights. And so here it's IO of nil. This I don't really know yet how to implement it, but the idea with this search all client is that at the end we're going to call search all clients here, passing the list of clients we got as the input of this function. So this is going to give us an IO of list of flights for all the clients, and then we can map it using search result. So really, so this is all the implementation we need. The only thing that is really tricky is this part, is the case where we do have at least one client. How do we search it? So let's think about it. So we have at least one client, which means that we can call search for it, right? So this will pass the parameter, or actually we can reuse the method search by client. It's already implemented. So if we do this, this is going to search for one client, handle the errors, and do everything we need. So this gives us an IO of list of flights, but we also need to use this potentially non-empty list of clients at the end. So one way to do this is to call this method recursively. So we could say search all clients with other clients. And this way we have two IOs returning a list of flights. Essentially it's the same thing that we had here. So we could copy paste this and slightly change the code. So here, instead of search by client for client 1, it's search by client for this head of the list. And here, instead of search by client for client 2, it's a recursive search. But essentially, it is the same thing, right? Let's run the test to see if we haven't broken anything. Oh, there is, oh yeah, okay, so at the moment, yeah, this needs to be a list of flights. So I shouldn't have created a search result at the moment. We just want to concatenate the list. We will create a search result at the end. So let's rerun it. Yeah, all the tests pass. Quite nice. Now, so this implementation has a couple of issues. First, it's not tail recursive. So we can verify it by adding a tail rec annotation here. You can see that it's not tail recursive because we do the recursive call and then we do something else after. So it's not tail recursive. We could re-implement, so this means that if the list is very big, so let's say 10,000 elements, just iterating over it will blow the stack. Now here we are fine with this because we have this assumption that in practice we'll never have like 10,000 clients. In practice we may have 100, 200 clients, but there will be never a case when we have 10,000 data providers. Or if it happens, it will be late in the future. We can always refactor this code later on. So potentially we are fine with a custom recursion. But one thing that is a bit annoying with this is the fact that here really this function, what it does is that it calls search by client for each client and then it aggregates the results together. So really what we do is that we call this function many times for every single item in the list, and then we merge them all together, which seems to be something that we'll do quite a lot in practice. So what will be nice is if we could use an extended method, a higher order function to capture this pattern. So let me show you how we could discover it. So let's ignore this test for now. We can, ignore this code. We can comment it out. And so what we would like to do ideally is that we have our list of clients over there, and we want to map over it and call search by client. So in other words, we have potentially many clients, and we want to search for each one of them. Now, if you look at the type we get as a result, it's really horrible. It's a list of IO of list of flight. So it doesn't make much sense. What does it mean? Let's try to translate it. It's a list, so it means it's a container which has potentially many items inside it. So it's potentially many IO, so many actions, and each action, when you run them, give us back a list of flights. Now, ideally, what we would like is an IO of list of flights, or at least, maybe let's write down the translation we would like to do. So at the moment, we have an list of IO of list of flight, and what we would like to get is an IO of list of flights. This will be the ideal. Now, this is probably going to be like quite a complex transformation. What we could do is to have an intermediate step where we take our list of IO of list of flights, but we're just going to, the real problem here is the fact that the IO is in between the two lists. If we were able to move the IO outside, so basically if we were able to swap the IO in the list, then this transformation would be quite simple. Because if we have an IO of list of flight, we can go inside the IO and flatten it all together, and it will work. The real problem is this translation from a list of IO into an IO of list. This is really the tricky part. And there is a method in the not in the Stern library, but in all IO implementation called sequence. So if you look at the companion object of IO, sequence does exactly this. It takes a list of IO of A and return an IO of list of A. So in other words, it takes several actions and return a single action that will return all the results. So if we call a sequence on this, then we get this IO of list of flights, and then we can map over it, flatten it. This will give us an IO of list of flights, and then we can call search results. And the code will be much nicer this way, right? The real problem is that we do need to have a sequence implemented. So let's have a look. Sequence, so it's a method of the companion object of IO that takes this list of IO and return an IO of list. So a typical example, you could imagine, if we have a method db.getUser that given a user ID gives us back an IO of user, let's imagine we code this method several times with different user ID. When you call sequence, you're going to get back an IO of list of user, and what this IO is going to do is when you call unsafe run on it, it will first fetch the first user, then fetch the second user, then fetch the third user, and if there is no error, it will repackage everything into a list, which is kind of exactly what we want. So now I will let you pause the video and try to implement sequence, and there are a couple of tests in the companion object. So please pause the video and give it a try. Okay, so to implement sequence, we can start again with a recursive approach. We can say, okay, actions is a list. It's a list, so it means it's an enumeration. We can do an exhaustive pattern match and go from one problems to two simpler ones. So the simple case is if the list of action is empty, then we're going to create a new IO that will return nil at the end, right? There is nothing else we can do. We can't produce any A. We need to return an empty list. Here, in this case, we want to do a for comprehension, where we'll say, okay, this will be like result 1. So head is an IO of A. So we'll say, okay, let's get the result of head. Let's call ourselves recursively. So let's say result 2 is this next. So next is, if you look at the type of next, it's a list of IO of A. So we can call ourselves recursively with next. And here we can concatenate them together. So if you want, what we've done here is exactly the code we've done inside of search flight service over there. Sorry, I removed it, but you probably remember inside this implementation we had a pattern match that was doing a recursive call. Here, in fact, in I/O, what we've done is exactly the same thing, except that we capture this general pattern and we apply it for everything. So the nice thing about it is that once it's implemented, we can reuse it everywhere. Now, let's try to run the test for it. In I/O test, there is one test for sequence. So what does this test does? It again uses this mutating variable technique that says the counter starts at 0. The first I/O add 2 to the counter and return it. Then the second I/O multiplies the counter by 3 and returns it. Then do -1 and returns it. So eventually when we run it, we expect to see 2, 6, 5, like 0 plus 2, 2 times 3, 6, 6 minus 1, 5, right? So let's run the test to see if it works. Oh, sorry, I'm running actually the wrong one. So let's run the I/O test. Cool, so it passes, nice. Now, as you can see here, we do have the same problem that we had in search flight service. This function is not tail recursive. If you look at this, the compiler tells us that sequence is not the last thing we do in the function. And for sequence, we do care about this because we don't have this background that we know that it's going to be called with a small list. Potentially, it can be called with a very large list. So here we do have to deal with this corner case. So what we can do to fix the problem is to re-implement this method using fold left, because fold left is guaranteed to be stack safe. It's implemented in the standard library in a stack safe way, either using a recursion but with a tail rec approach, or using a for loop with a mutating variable. It doesn't really matter. We kind of trust the standard library to have it implemented correctly. So how are we going to use fold left here? Well, fold left takes a default value, but the default value is what we return in case the action is nil, so we can copy paste this. But as you might remember from previous chapters, there is a problem of a type inference issue with fold left. So here we really have to be explicit and say that nil is actually an empty list of A. So we need to do that really to help the compiler figure it out the right type in this particular case. Now this, so here we have a state, and here we have an action. And so this is the combined function. And the combined function is basically what we have here. So we say instead of head is action, and instead of doing the recursive call, we take state. That's it. Let's rerun the test. Oh, it fails. So let's have a look. So what does it say? So we expected to see 2, 6, 5, but we got -1, -3, -1. So what actually seems is that we are executing the actions backward, because if we do 0, -1 is -1, times 3, -3, plus 2, -1. So it seems that when we implemented sequence, we are not combining the actions in the right order. And it's actually very difficult to see. I get it wrong all the time. But you see state represent the actions we have already processed. So basically it's the prefix of the list. So at the moment what we do, because we execute action first and then the prefix, is the same as starting to execute the action by the end of the list. So it's very subtle, but the good thing is that our tests were able to catch it. So what we need to do is to swap the order inside of the for comprehension. So we first want to execute state being the prefix of the list, and then we want to execute action in order to do it in the right order. Okay, let's rerun the test. So normally it should have fixed it. No, it hasn't. So it's a bit better. Now we do get the right number, so we do get 2, 6, 5, but they are not in the correct order. So you can see 5 is supposed to be at the end, but now it's at the beginning, 6 in the middle, and 2 was supposed to be at the beginning, but it's at the end. So what happens here, it's again another tricky thing with sequence, is that result 1 is whatever is produced by action, but we prepend it to the list. But if you want, result 2 is the prefix of the list. Here is the result we have already seen. So maybe it's actually not really helpful to say result 2 and result 1. Maybe let's reverse it. Maybe this way it's maybe slightly more readable. Here you can see that result 2 is supposed to come after result 1, but we prepend it to the list. So what we need to do actually is to say append it at the end of the list. Now if you rerun the test, it should work. Cool. So as you see, previously we were running the action in the correct order, but we would accumulate the result in the wrong order. It's very tricky to get it right. That's why you really need to have tests for this. At least the good thing with fold left is that we have the guarantee of the stack safety. Now, a small optimization we can do here is that adding at the end of a list is inefficient. So if we had a vector, it would be completely fine, because adding at the end of a vector is, it doesn't take much more time than at the beginning. But for a list, it's really inefficient. So what we want to do here is actually revert back and say, okay, we want to prepend, because prepend we know that is fast, and then at the end, we are going to reverse everything. So this is a very small performance optimization. We are adding the element in the wrong order, and at the end we reverse everything to put it back in the correct order. This is faster to do it the other way around. Let's rerun the test. It works. Cool. Now as you can see, it's very tricky to get sequence right. We have to worry about tail recursion, about having stack safety. We have to worry about executing the actions in the right order, collecting the results in the right order. Personally, I always get it wrong. That's why it's very crucial to have a good test suite to catch these kind of errors. Now, the good thing is that once we have it implemented once and for all, we can reuse it everywhere. And this is what we did in From Clients. Now the code is much clearer. Essentially, we have one function to describe how to fetch flights from a single client. This is search by client. And then we use the generic functions map and sequence to repeat this process for the entire list and squash the actions together. So in summary, for comprehensions are great when we want to combine a few IOs sequentially. This is what we did in From to Clients. But we need to use map and sequence when we don't know in advance how many IOs we'll have. For example, when they're in a list or any other kind of data structures. Now there is one last thing that annoys me about this implementation. It is the fact that we mix both methods from the IO companion object, such as io.sequence, and methods from the IO class, such as map. Ideally, it will be nice to use like an OOP syntax for all the methods. So it would be nice to do .sequence after map, something like this. And surprisingly, it works, but it shouldn't, because list doesn't have a method sequence. List doesn't know about IO. But it only works here because I define an extension method for this particular scenario. So let's have a look. So if you click on sequence, it will redirect you to a package object inside of FP. And so in this package object, I use this extension method technique that lets us add methods to a class after it has been defined. For example, we can't add normal methods to the class list because list is defined in the standard library. So we can't go and open the class list and add methods to it. We need to use this extension method technique. So in order to define an extension method, we need to define an implicit class. So this implicit keyword is important. And this class needs to take a single argument. This is the type that we want to extend. For example, here that we said that we want to extend the type list of IO of something. Second, we need to define method within this implicit class. These are the methods we want to add to the type. For example, here we add the method sequence and parsequence to the list of IO. I'll put some documentation about this technique below the video. In particular, you will see that the syntax is completely different in Ch03. Now, if we go back to From Clients, there is just one last refactoring that I would like to show you. Is the fact that map followed by sequence is an extremely common pattern. So functional programmers came up with an alias for it. It's called traverse. So if you want, you can replace map by traverse and remove sequence, and it should all work. Let's run the test for it, for example. We see that it should all pass. Yes, it does. So if you want, traverse is not a particularly great name. It's not really consistent with the rest. Because when you have map plus flatten followed by flatten, it's called flat map. When we've seen also map followed by fold, it was called fold map. So you could have thought that map followed by sequence should have been called like sequence map or sec map, but it turned out that it's called traverse. Now it's not really consistent, but it's quite a common name, so let's keep using it. In summary, today we went from an implementation that uses only 2 data providers to an implementation that uses an arbitrary number of clients. So it perfectly suits our use case of reading a list of clients from a config file and combining all these clients together. So it took us some time to get there because we went through a long series of refactoring to clean up the code. These were not necessary. We could have stopped at the first recursive implementation. However, the benefit of this approach is that we arrive at a very concise and clear solution, at least once you get used to traverse. Additionally, we can be quite confident that our code is correct because this version is mostly based on standard and well-tested methods such as map, traverse, and handle error width, rather than custom functions written by us for this particular problem. Cool, so that's it for today. I suggest that we take a break. In the next couple of videos, we'll look at improving the performance of from clients by fetching data concurrently. See you soon.